An industrial robot is a robot system used for manufacturing. Industrial robots are automated, programmable and capable of movement on two or more axes. Typical applications of robots include welding, painting, assembly, pick and place for printed circuit boards, packaging and labeling, palletizing, product inspection, and testing, all accomplished with high endurance, speed, and precision. They can help in material handling and provide interfaces. Types and features. The most commonly used robot configurations are articulated robots, SCARA robots, delta robots and Cartesian coordinate robots. In the context of general robotics, most types of robots would fall into the category of robotic arms. Robots exhibit varying degrees of autonomy. Some robots are programmed to faithfully carry out specific actions over and over again without variation and with a high degree of accuracy. These actions are determined by programmed routines that specify the direction, acceleration, velocity, deceleration, and distance of a series of coordinated motions. Other robots are much more flexible as to the orientation of the object on which they are operating, or even the task that has to be performed on the object itself, which the robot may even need to identify. For example, for more precise guidance, robots often contain machine vision subsystems acting as the visual senses. Linked to powerful computers or controllers, artificial intelligence, or what passes for it, is becoming an increasingly important factor in the modern industrial robot. History of industrial robotics. The earliest known industrial robot, conforming to the ISO definition, was completed by Bill Griffith P. Taylor in 1937 and published in Meccano magazine, March 1938. The crane-like device was built almost entirely using Meccano parts, and powered by a single electric motor. 5 axes of movement were possible, including grab-and-grab rotation. Automation was achieved using punched paper tape to energize solenoids, which would facilitate the movement of the crane's control levers. The robot could stack wooden blocks in pre-programmed patterns. The number of motor revolutions required for each desired movement was first plotted on graph paper. This information was then transferred to the paper tape, which was also driven by the robot's single motor. Chris Shute built a complete replica of the robot in 1997. George Devil applied for the first robotics patents in 1954. The first company to produce a robot was Animation. Animation was founded by Devil and Joseph F. Engelberger in 1956, and the first robot, Animate, was invented by Norman Heroux and was based on Deville's original patents. Animation robots were also called programmable transfer machines, since the main use at first was to transfer objects from one point to another, less than a dozen feet or so apart. They used hydraulic actuators and were programmed in joint coordinates, i.e., the angles of the various joints were stored during a teaching phase and replayed in operation. They were accurate to within 1/10,000th of an inch. Animation later licensed the technology to Kawasaki Heavy Industries and GKN Manufacturing Animates in Japan and England respectively. For some time Animation's only competitor was Cincinnati Milacron Inc. of Ohio. This changed radically in the late 1970s when several big Japanese conglomerates began producing similar industrial robots. In 1969, Victor Scheiman at Stanford University invented the Stanford Arm, an all-electric, 6-axis articulated robot designed to permit an arm solution. This allowed it accurately to follow arbitrary paths in space and widened the potential use of the robot to more sophisticated applications such as assembly and welding. Scheiman then designed the second arm for the MIT AI lab, called the MIT Arm. Chinaman, after receiving a fellowship from Unimation to develop his designs, sold those designs to Unimation, who further developed them with support from General Motors and later marketed it as the programmable universal machine for assembly. Industrial robotics took off quite quickly in Europe, with both AB Robotics and KUKA Robotics bringing robots to the market in 1973. AB Robotics introduced IRB6, among the world's first commercially available all-electric microprocessor-controlled robot. The first two IRB6 robots were sold to Magnusson in Sweden for grinding and polishing pipe bends and were installed in production in January 1974. Also in 1973, KUKA Robotics built its first robot, known as FAMULUS, also one of the first articulated robots to have 6 electromechanically driven axes. Interest in robotics increased in the late 1970s and many U.S. companies entered the field, including large firms like General Electric and General Motors. U.S. startup companies included Automatrix and Adept Technology, Inc. At the height of the robot boom in 1984, Unimation was acquired by Westinghouse Electric Corporation for $107 million US dollars. Westinghouse sold Unimation to Stobli-Faverges SCA of France in 1988, which is still making articulated robots for general industrial and cleanroom applications, and even bought the robotic division of Bosch in late 2004. Only a few non-Japanese companies ultimately managed to survive in this market, the major ones being Adept Technology, Stobli Unimation, the Swedish-Swiss company AB SCA Brown Boveri, the German company KUKA Robotics, and the Italian company Komatsu. Technical description: defining parameters. Number of axes. 2 axes are required to reach any point in a plane. 3 axes are required to reach any point in space. To fully control the orientation of the end of the arm, 3 more axes are required. Some designs trade limitations in motion possibilities for cost, speed, and accuracy. Degrees of freedom. This is usually the same as the number of axes. Working envelope, the region of space a robot can reach. Kinematics, the actual arrangement of rigid members and joints in the robot, which determines the robot's possible motions. Classes of robot kinematics include articulated, Cartesian, parallel, and SCARA. Carrying capacity, a payload, how much weight a robot can lift. Speed, how fast the robot can position the end of its arm. This may be defined in terms of the angular or linear speed of each axis, or as a compound speed, i.e., the speed of the end of the arm when all axes are moving. Acceleration, how quickly an axis can accelerate. Since this is a limiting factor, a robot may not be able to reach its specified maximum speed for movements over a short distance or a complex path, requiring frequent changes of direction. Accuracy, how closely a robot can reach a commanded position. When the absolute position of the robot is measured and compared to the commanded position, the error is a measure of accuracy. Accuracy can be improved with external sensing, for example a vision system or infrared. See robot calibration. Accuracy can vary with speed and position within the working envelope and with payload. Repeatability, how well the robot will return to a programmed position. This is not the same as accuracy. It may be that when told to go to a certain XYZ position that it gets only to within 1 mm of that position. This would be its accuracy, which may be improved by calibration. But if that position is taught into controller memory and each time it is sent there it returns to within 0.1 mm of the taught position, then the repeatability will be within 0.1 mm. Accuracy and repeatability are different measures. Repeatability is usually the most important criterion for a robot and is similar to the concept of precision in measurement. See accuracy and precision. ISO 9283 sets out a method whereby both accuracy and repeatability can be measured. Typically, a robot is sent to a taught position a number of times and the error is measured at each return to the position after visiting 4 other positions. Repeatability is then quantified using the standard deviation of those samples in all 3 dimensions. A typical robot can, of course, make a positional error exceeding that, and that could be a problem for the process. Moreover, the repeatability is different in different parts of the working envelope and also changes with speed and payload. ISO 9283 specifies that accuracy and repeatability should be measured at maximum speed and at maximum payload, but this results in pessimistic values, whereas the robot could be much more accurate and repeatable at light loads and speeds. Repeatability in an industrial process is also subject to the accuracy of the end effector, for example a gripper, and even to the design of the fingers that match the gripper to the object being grasped. For example, if a robot picks a screw by its head, the screw could be at a random angle. A subsequent attempt to insert the screw into a hole could easily fail. These and similar scenarios can be improved with lead-ins, e.g., by making the entrance to the hole tapered. Motion control. For some applications, such as simple pick-and-place assembly, the robot need merely return repeatably to a limited number of pre-taught positions. For more sophisticated applications, such as welding and finishing, motion must be continuously controlled to follow a path in space, with controlled orientation and velocity. Power source. Some robots use electric motors, others use hydraulic actuators. The former are faster, the latter are stronger and advantageous in applications such as spray painting, where a spark could set off an explosion. However, low internal air pressurization of the arm can prevent ingress of flammable vapors as well as other contaminants. Drive. Some robots connect electric motors to the joints via gears. Others connect the motor to the joint directly. Using gears results in measurable backlash, which is free movement in an axis. Smaller robot arms frequently employ high-speed, low-torque DC motors, which generally require high gearing ratios. This has the disadvantage of backlash. In such cases, the harmonic drive is often used. Compliance. This is a measure of the amount in angle or distance that a robot axis will move when a force is applied to it. Because of compliance, when a robot goes to a position carrying its maximum payload, it will be at a position slightly lower than when it is carrying no payload. Compliance can also be responsible for overshoot when carrying high payloads, in which case acceleration would need to be reduced. Robot programming and interfaces. The setup or programming of motions and sequences for an industrial robot is typically taught by linking the robot controller to a laptop, desktop computer or network. A robot and a collection of machines or peripherals is referred to as a work cell or cell. A typical cell might contain a parts feeder, a molding machine and a robot. The various machines are integrated and controlled by a single computer or PLC. How the robot interacts with other machines in the cell must be programmed, both with regard to the positions in the cell and synchronizing with them. Software. The computer is installed with corresponding interface software. The use of a computer greatly simplifies the programming process. Specialized robot software is run either in the robot controller or in the computer, or both, depending on the system design. There are 2 basic entities that need to be taught: positional data and procedure. For example, in a task to move a screw from a feeder to a hole, the positions of the feeder and the hole must first be taught or programmed. Secondly, the procedure to get the screw from the feeder to the hole must be programmed along with any I/O involved. For example, a signal to indicate when the screw is in the feeder ready to be picked up. The purpose of the robot software is to facilitate both these programming tasks. Teaching the robot positions may be achieved a number of ways. Positional commands: the robot can be directed to the required position using a GUI or text-based commands in which the required XYZ position may be specified and edited. Teach-pendant robot positions can be taught via a teach-pendant. This is a handheld control and programming unit. The common features of such units are the ability to manually send the robot to a desired position, or inch, or jog, to adjust to position. They also have a means to change the speed, since a low speed is usually required for careful positioning, or while test running through a new or modified routine. A larger emergency stop button is usually included as well. Typically, once the robot has been programmed, there is no more use for the teach pendant. Lead by the nose is a technique offered by many robot manufacturers. In this method, one user holds the robot's manipulator, while another person enters a command which energizes the robot, causing it to go limp. The user then moves the robot by hand to the required positions and/or along a required path, while the software logs these positions into memory. The program can later run the robot to these positions or along the taught path. This technique is popular for tasks such as paint spraying. Offline programming is where the entire cell, the robot, and all the machines or instruments in the workspace are mapped graphically. The robot can then be moved on screen and the process simulated. A robotics simulator is used to create embedded applications for a robot, without depending on the physical operation of the robot arm and end effector. The advantages of robotics simulation is that it saves time in the design of robotics applications. It can also increase the level of safety associated with robotic equipment, since various what-if scenarios can be tried and tested before the system is activated. Robot simulation software provides a platform to teach, test, run, and debug programs that have been written in a variety of programming languages. Robot simulation tools allow for robotics programs to be conveniently written and debugged offline with the final version of the program tested on an actual robot. The ability to preview the behavior of a robotic system in a virtual world allows for a variety of mechanisms, devices, configurations, and controllers to be tried and tested before being applied to a real-world system. Robotics simulators have the ability to provide real-time computing of the simulated motion of an industrial robot using both geometric modeling and kinematics modeling. Others, in addition, machine operators often use user interface devices, typically touchscreen units, which serve as the operator control panel. The operator can switch from program to program, make adjustments within a program, and also operate a host of peripheral devices that may be integrated within the same robotics system. These include end effectors, feeders that apply components to the robot, conveyor belts, emergency stop controls, machine vision systems, safety interlock systems, barcode printers, and an almost infinite array of other industrial devices which are accessed and controlled via the operator control panel. The teach pendant PC is usually disconnected after programming, and the robot then runs on the program that has been installed in its controller. However, a computer is often used to supervise the robot and any peripherals, or to provide additional storage for access to numerous complex paths and routines. End-of-arm tooling. The most essential robot peripheral is the end effector, or end-of-arm tooling. Common examples of end effectors include welding devices, spray guns, and also grinding and deburring devices, and grippers. Another common means of picking up an object is by vacuum. End effectors are frequently highly complex, made to match the handled product, and often capable of picking up an array of products at one time. They may utilize various sensors to aid the robot system in locating, handling, and positioning products. Controlling movement. For a given robot, the only parameters necessary to completely locate the end effector of the robot are the angles of each of the joints or displacements of the linear axes. However, there are many different ways to define the points. The most common and most convenient way of defining a point is to specify a Cartesian coordinate for it, i.e., the position of the end effector in mm in the x, y, and z directions relative to the robot's origin. In addition, depending on the types of joints a particular robot may have, the orientation of the end effector in yaw, pitch, and roll, and the location of the tool point relative to the robot's faceplate must also be specified. For a jointed arm, these coordinates must be converted to joint angles by the robot controller, and such conversions are known as Cartesian transformations, which may need to be performed iteratively or recursively for a multiple axis robot. The mathematics of the relationship between joint angles and actual spatial coordinates is called kinematics. See robot control. Positioning by Cartesian coordinates may be done by entering the coordinates into the system or by using a teach pendant which moves the robot in x, y, z directions. It is much easier for a human operator to visualize motions up, down, left, right, etc., than to move each joint one at a time. When the desired position is reached, it is then defined in some way particular to the robot's software in use, e.g. P1, P5 below. Typical programming. Most articulated robots perform by storing a series of positions in memory and moving to them at various times in the programming sequence. For example, a robot which is moving items from one place to another might have a simple pick-and-place program similar to the following. Define points P1, P5 safely above workpiece, 10 cm above bin A. At position to take part from bin A. 10 cm above bin B. At position to take part from bin B. Define program. Move to P1. Move to P2. Move to P3. Close gripper. Move to P2. Move to P4. Move to P5. Open gripper. Move to P4. Move to P1 and finish. For examples of how this would look in popular robot languages, see Industrial Robot Programming. Singularities. The American National Standard for Industrial Robots and Robot Systems Safety Requirements defines a singularity as a condition caused by the collinear alignment of two or more robot axes resulting in unpredictable robot motion and velocities. Quote, "It is most common in robot arms that utilize a triple roll wrist. This is a wrist about which the three axes of the wrist, controlling yaw, pitch, and roll, all pass through a common point. An example of a wrist singularity is when the path through which the robot is traveling causes the first and third axes of the robot's wrist to line up. The second wrist axis then attempts to spin 180 degrees in zero time to maintain the orientation of the end effector. Another common term for this singularity is a wrist flip. The result of a singularity can be quite dramatic and can have adverse effects on the robot arm, the end effector, and the process. Some industrial robot manufacturers have attempted to sidestep the situation by slightly altering the robot's path to prevent this condition. Another method is to slow the robot's travel speed, thus reducing the speed required for the wrist to make the transition. The ANSI rear has mandated that robot manufacturers shall make the user aware of singularities if they occur while the system is being manually manipulated. A second type of singularity in wrist-partitioned vertically articulated 6-axis robots occurs when the wrist center lies on a cylinder that is centered about axis 1 and with radius equal to the distance between axes 1 and 4. This is called a shoulder singularity. Some robot manufacturers also mention alignment singularities, where axes 1 and 6 become coincident. This is simply a subcase of shoulder singularities. When the robot passes close to a shoulder singularity, joint 1 spins very fast. The third and last type of singularity in wrist-partitioned vertically articulated 6-axis robots occurs when the wrist center lies in the same plane as axes 2 and 3. These kinematic singularities are closely related to the phenomena of gimbal lock, which has a similar root cause of axes becoming lined up. A video illustrating these three types of singular configurations is available here. Note that there is another type of singularities, the topological singularities. These are topological singularities of the configuration space of the robot. Whereas these are harder to compute and understand, they have much more profound impact on the robot's motion. Market structure. According to the International Federation of Robotics study World Robotics 2014, there were between 1,332,000 and 1,600,000 operational industrial robots by the end of 2013. This number is estimated to reach 1,946,000 by the end of 2017. For the year 2011, the IFR estimates the worldwide sales of industrial robots with $8.5 billion, including the cost of software, peripherals and systems engineering. The annual turnover for robot systems is estimated to be $25.5 billion in 2011. The Japanese government estimates the industry could surge from about $5.2 billion in 2006 to $26 billion in 2010 and nearly $70 billion by 2025. In 2005, there were over 370,000 operational industrial robots in Japan. A 2007 National Technology Roadmap by the Trade Ministry calls for 1 million industrial robots to be installed throughout the country by 2025. Estimated worldwide annual supply of industrial robots